This video will discuss significant figures, which are also called significant digits, and how they are important in measurement when we record data. So significant figures, what are they? They are the numbers, when you measure something, that include all measured and estimated values. And there are rules for determining the number of sig figs, or significant figures, or significant, I'm just going to say sig figs because it's easier to say. They all mean the same thing. Rules are all non-zeros are significant. And we'll talk about these individually. Leading zeros are not significant, and those are the zeros at the beginning of a number, like the placeholder zeros. Ending zeros are not significant if our number does not have a decimal. So those are the rules. Also, I didn't make it in the list here, but if you have zeros that are between two other numbers, like sandwich zeros, they're also always significant. The best way to learn it is just to practice. So we will go through some numbers that have zeros in them, and we'll talk about which ones are significant and which ones are not, and how many sig figs their number has. So the first number here is 0.001, and this measurement has one sig fig. These zeros are not significant because they're leading. Leading zeros are not significant. It doesn't mean that they're not important. We have to have them in our number. They're placeholders. But only the one is a sig fig, so this only has one sig fig. In the next number here, it's 2,000. Note that there is no decimal in this number. So the zeros here are placeholders. They're ending zeros, and they're not significant. So just the 2 is a significant digit here, and it has 2,000 has one sig fig. This one's a little bit more complicated. We've got 0.00. These are leading zeros. They're not significant. And then a 1, and then a 0. This 0 here is a sig fig because it's at the end, but our number has a decimal. So it is a significant digit. It was picked on purpose, and that's what that means. So this number here has 2 sig figs. So again, the first has 1, this has 1 sig fig, and this one has 2. So for practice, there's another set of numbers here, a little bit more complicated, other little bit more variety. Shut off your video, go through and just count the number of sig figs, and then turn it back on and we will discuss. Okay, so the answers here are 67.09. All the digits here are significant, and there are 4 of them. There's no leading zeros, there's no ending zeros. 0.052, this number has 2 sig figs. The 0.0 at the beginning, those are leading. They're placeholders. They're not significant. Again, it doesn't mean that they're not important. We can't leave them off. We need them in our number, but they're not measured values. Okay, the next one has 2 sig figs, 470, comma, 000. Because there's no decimal, all these 4 zeros here are ending zeros. They're just placeholders. And my number just has 2 sig figs. And then the last one, this has 5 sig figs, so 4.9050. All the numbers are significant. Because I have a decimal, my ending 0 over here is significant. So they're all sig figs. The only zeros that are not significant are the leading zeros and possibly the ending ones. I call this a sandwiched 0. It's in between 2 other numbers. This is always a sig fig too. Okay, exact numbers are counted numbers, and they're different from measurements because they're not estimated. We know the exact number. So when we're doing calculations, and and we want to pay attention to sig figs for our calculation purposes, we're not going to count exact numbers as, we're not going to let them determine the sig figs in our answers. So examples of exact numbers are 24 students. We're not saying that the number of students is somewhere between 20 and 30. We know that it is exactly 24. And that is an exact number. It's not a measured number. So 175 books. Again, we did not estimate this 5. We know it to be exactly 175. And this makes a difference when we talk about calculations, because you want to be able to look at significant digits and decide how to round at the end. So another way to say this is don't round based on counted numbers. That's probably an easier way to think about that. All right, so let's do some practicing for measurement. What I'm going to do is I'm going to go through these in quite a bit of detail and talk about how you would measure these values, what would be acceptable answers, what would be not acceptable. And these, once you get used to it, it's not hard. It can be a little bit tricky at first, and it's usually new to most students. So the first one is a beaker, and it has a liquid in it. And let's look at the volume here. So you always want to look at the markings on your beaker and say, okay, what do each of these markings mean? And what is my volume going to be based on those? So one thing you want to realize is this is a 40, and this is a 60, and this little dash in the middle here is a 50. Not every marking is going to have a number, and that's okay. It's still 50 even without writing the number 50, so it counts. So what do we know about this volume? We know that it is bigger than 40 and it's less than 50, okay? And we are going to estimate what we think that second digit is. And I've estimated 46 milliliters. That's totally fine. If you were looking at this, you might say, that looks to me like it's 47. And that would be okay also. Either one of these answers are perfectly acceptable. They have the right number of digits based on the glassware, which is the most important thing. You could say 45, that seems like a little bit low for this measurement, but it's still acceptable with this glassware. Let's see, I want to back up a little bit. So before I go on, what if I said, I say 46, you say 47. What if I said 46.5? 46.5 would be incorrect because we don't have that kind of precision with this glassware. All we know with our measurement with this glass, or with this beaker, is that it's somewhere between 40 and 50. So we can't be more precise than this. This last digit is our estimated digit, and we cannot have any more digits than this. So the next one is a ruler, and what do we know for sure? So this is 1.0. This dash here is 1.5. So this little dash, that's a 1.1, 1.2, 1.3, 1.4. What do we know? We know that our measurement is between 1.3 and 1.4. So you could say it's 1.34, or you could say it's 1.35. Either one of these would be okay. It has to have this number of digits based on this ruler, and that's really the important thing here. How many numbers does your measurement have to have? The device that you're using to measure will tell you that. 1.33. Yeah, I guess that would be okay. I mean, it's sometimes hard to, when they're really close together, you just kind of make your best guess. Sometimes they get so close together that you just call everything, it's about halfway, and it's like, 0.5. But either one of these would be okay. Okay, so the last one is a thermometer. And what do we know about this measurement? So the red line is what we're measuring. This one's 21. This one's 22. All I know for sure is that it's somewhere between 21 and 22. And we are going to estimate that last digit. So I wrote 16 here. That was a mistake. This should be 21. Should be 21.5. That would be fine. 21.4 and 21.6. Any one of these would be okay. Pretend like I put a 21 there. And yeah, don't know what I was thinking. Okay, why does this matter? Isn't 2.00 the same as 2? What's confusing about this is when you put 2.00 into a calculator, the calculator turns it into a 2. And that, I think, is maybe what causes a lot of confusion with students, and they don't see the importance. But it's not the same, because 2.00 means that this final 0 was my estimated digit, and 2 is somewhere between 1 and 3, and that's it. So 2.00, because this was my estimated digit, what I know is that my number is between 1.99 and 2.01, and that is a really narrow range, and I know that number pretty precisely. 2, on the other hand, is somewhere between 1 and 3. So more precise number, and I show that with more sig figs. 2.00 has 3 sig figs, and 2 just has 1 sig fig. Okay, scientific notation. Hopefully you're somewhat familiar with it. It's a number formatted as a power of 10. It's used for very large and very small numbers. And we move the decimal over into the right spot. The decimal always is in between the first and the second non-zero numbers. And the number of times that we move the decimal over, that's the power that we raise it to. So for example, 369,000, the decimal would start out here. And we would move it over 5 times to get it between the 3 and the 6. So our number is raised to the power of 5. If the number is bigger than 1, the power is going to be positive. So it's 10 to the positive 5. One quick note about scientific notation. Note that we don't include the zeros in our number in scientific notation. If you drop the zeros when you put a number in scientific notation, those zeros were not sig figs. So if you're ever not sure about sig figs, think about putting it in scientific notation, and if they are placeholders, then it'll help you just realize that they're not sig figs. Okay, going the other way. If you're given a number in scientific notation, 2.4 times 10 to the 8, we're going to move the decimal over 8 times. And this is a big number. It's bigger than 1. So the 8 is a positive power, so it's 10 to the positive 8. On the other hand, the next number is smaller than 1. So we're going to move the decimal over. Again, we're going to move this over 6 times, but because we're moving the decimal to the right, to get it in the right spot, it's going to go between the 7 and the 1. The power is negative. So it's 7.12 times 10 to the negative 6. And that's because it's a small number, it's less than 1. And again, zeros that we get rid of when we put a number into scientific notation, those are leading zeros and they are not sig figs. And then the last one, we are given 5.0 times 10 to the negative 4. So we're going to move the decimal to the left, and it's going to be 0.00050. Because this 0 follows a decimal, it is a sig fig. And so we keep it in our final number. How to use a calculator with scientific notation. What you're going to want to do is use, depending on what calculator brand you have, you're going to use a button that's the EE button or the EXP button to put your number in scientific notation. I will go over this in a Zoom session, in a Zoom meeting. I'll have everyone make sure that you have your calculators and we'll do them all together. What you don't want to use is the times 10 to the caret. Like, don't put these functions all in separately. It will work sometimes, but there are times when it doesn't work, and it's really hard to explain when it doesn't work. So the best thing to do is just to use your calculator like it's meant to be used, and that's to use the scientific notation function. Some calculators have other symbols instead of these. If you have a calculator like that, I will work with you individually. And you want to get your own calculator and use it to practice. Please don't just use your phone or your laptop calculator. They're not very good scientific calculators. And you will find it easier to do calculations if you get a real calculator. So rules for sig figs in calculations. So now we're going to combine these two ideas, sig figs and calculations. It's important to keep track of sig figs because when you calculate, the answer should reflect the precision of the measurements that went into the calculation. You cannot increase precision by plugging a number into a calculator. So there's two rules. The first rule is for addition and subtraction, and it says that we're going to round the final answer to the least precise place value. So to round for addition and subtraction, we're going to look at place value. And the easiest is just to give you an example. So 5.9 plus 7.2943. Look at the place value of both of the numbers that go into your problem. So 5.9, this 9 is in the tenths place, and 7.2943, this 3, I don't really want to go into how to label things, but it's much more precise. It's 4 digits past the decimal. So the 9 is less precise because it's only 1 digit past the decimal. So our answer cannot be more precise than this. It has to end with this place value. So when we plug the whole thing into the calculator, which is what I want you to do, the calculator spits out this number. However, this 1 in this position is the last place value that my answer can have because it cannot be more precise than the number that goes into it. So I have to round to this place value, and because it's followed by a 9, my 1 is going to round up to a 2, and then the final answer is going to be 13.2. So we're just going to look at place value here. Round to the least precise place value. We don't actually do a lot of addition and subtraction, so we don't use this rule. We use it sometimes, but not so often. The next rule is much more common. We do a lot more multiplication and division. And this rule says that we're going to round our answer to the lowest number of sig figs. This is an easier one to use, and most students are more comfortable doing this because we do it a lot. So plug everything into your calculator. In this case, 56.195 times 9.4. Plug the whole thing in. And the answer in your calculator is 528.233. I recommend that you first write down like the whole number, or a lot of more digits than you need. And then you go back and you look at your two numbers that go into your calculation. 56.195 has 5 sig figs. 9.4 has 2 sig figs. This has the lowest number of sig figs, so our answer has to have 2 sig figs. That's pretty much it. So we look at our answer, and then we say, okay, we have to round that to 2 sig figs. So 5, and then the 2, which is going to round up because it's followed by an 8. And then the answer is going to be 530. Don't forget that you need the 0 here. It's not a sig fig, but it's a placeholder and it's necessary. Without the 0, we would round it to just 53, which would be completely incorrect. So make sure that you're, when you round, that you turn the, that you put in the placeholder zeros as you need to. So last thing, for multi-step calculations, normal order of operations rules apply. So the rules that you learned in math for order of operations, hang on to those. We don't use a lot of multi-step calculations that combine addition and subtraction and multiplication, so it's not such an issue. But the big thing for us is that don't round until you're done with all the calculations. So don't round in the middle. If you're gonna do some math and then take your answer and then do another calculation with it, do all the calculations and then round your final answer. Otherwise, you can get what's called rounding errors.